Okay, let's get started. So welcome to the colloquium today. And today we have a great pleasure to have the Chuan-Jui from ASIAA from our own institute to speak about his research about the supernova. And I just apologize because this is a sudden change. Originally, we want to have a in-person colloquium. However, last week was some COVID situation in the summer students. So because we want to summer students to have chance to join the colloquiums, so we move to online. And I get a brief introduction to Chuan-Jui. And Chuan-Jui got his PhD from NTU in 2018. And he became the postdoc researcher at the ASIAA. At the beginning, we did like a substitutional research position for the military service, and later become formal employee for SIA. And he got the award from this military service for some kind of outstanding performance in the job, in the research. And he also got the publication award from MOST. And starting this year, he awarded this AS regular postdoctoral fellows. And it's basically, so Chuan-Jui worked on the observational study of the supernova, focusing on type 1a. And today, he will be share with us about his research on this type 1a supernova arrangement and to binary and some love story, probably some romantics. Okay, I leave the stage to Chuan-Jui. So Chuan-Jui, please go to speak.
Okay. So I share my screen.
Okay.
So thank you all for coming and thanks for the invitation. So from yesterday, my Facebook and email box are full of JWST new images, and those images are amazing. Today I will also show some beautiful images, so I hope you can enjoy it. So my research goal is to understand the nature of type 1a supernovae. It is believed that type 1a supernovae are binary systems before the supernova explosion. So to probe the nature of type 1a supernovae, I searched for the clues in the remains of the supernova explosions called supernova remnants to figure out what kind of binary system type 1a supernovae were before the explosions. So this is a Mandarin version of my title. I wrote an article to ASIAA Scientific Highlight, and this title was Mei Ying's idea. She helped me think of about this title, and it's more romantic. So type 1a supernovae have been used as standardizable candles to probe the cosmological distance. So the background images, there is a type 1a supernova, and there is a galaxy. You can see how bright a type 1a supernova is. And this leads to the revelation of dark energy and the award of Nobel Prize in Physics 2011 to the astronomers for the discovery of the accelerating expansion of the universe through observations of distant supernovae. But it's quite embarrassing that type 1a supernovae are not fully understood. We know there are two origins of supernovae: core collapse supernovae and type 1a supernovae. Core collapse supernovae originates from massive stars. And massive stars are luminous and detectable in the pre-explosion images. So sometimes we can compare the pre-explosion images with the post-explosion images, and we can identify which massive star exploded as a core collapse supernova. However, Type 1a supernovae originate from white dwarfs, and white dwarfs are too faint to be identified. So in general, there are two contrasting scenarios for Type 1a supernovae: accreting white dwarf or merger of two white dwarfs. So in the accreting scenario, it requires a white dwarf and a companion. The white dwarf will accrete matters from the companion until the mass of white dwarf reach the Chandrasekhar mass, and it will explode as a Type 1a supernova. In the merger scenario, two white dwarfs will merge together and explode as a Type 1a supernova. So the question is, accreting or merger, or both they are correct? So to answer this question, I would like to introduce the evolution of an observable Type 1a supernova. So at the very beginning, there is an initial binary system. We don't know it's accreting or merger, or both they are correct. And it will explode as a Type 1a supernova. And then we can take the spectrum and to observe the light curves. And after the supernova shocks going through the interstellar median, a supernova remnant is formed. And this is the remains of the explosion. So to answer the question, is accreting or merger, people can search for some binary systems that are candidates will possibly become a Type 1a supernova. Or they can take the spectrum or light curves of the explosion and to see whether there are some signatures to differentiate accreting or merger scenarios. For example, the Professor Pan Yancheng in National Central University, he is working on also prove the nature of Type 1a supernovae. And his work focused on using the entire galaxy to constrain the nature of Type 1a supernovae. And it's the second and the third stage here. And my works focus on the fourth stage here, that I search for clues in the supernova remnants to probe the nature of Type 1a supernovae. So how to differentiate accreting and merger scenarios? So in the accreting scenario, there is a white dwarf and a companion, and the white dwarf will accrete matter from the companion. So you can see here is a simulation done by the Professor Pan Guoquan in National Tsinghua University. From left to the right is with respect to the time. So we can simulate that how the supernova ejecta make impact on the companion, and simulate the interactions between the supernova ejecta and the companion. The mass of the companion will be stripped, and and after the impact of supernova, the companion will run away. But in simulation, this companion is predicted to survive the supernova explosion, and we call it the surviving companion. So you can see the upper panel is the simulation, and the lower panel is the observation. If a surviving companion or circumstellar median is found, the origin of accreting white dwarf is affirmed. The circumstellar median is the material that produced from the mass loss of the interactions between the supernova ejecta and the companion. And the surviving companion may be identified by its runaway velocity, or faster rotation, chemical pollution, or some strange color and luminosity. So some peculiar physical properties that are different from other stars. So if we want to search for a surviving companion within a Type 1a supernova remnant, the first thing we need to define a supernova explosion center. Usually, people use the multi-wavelength boundaries of a type 1 supernova remnant to define a supernova explosion site. And we will use the supernova remnant's age and the predicted surviving companion's velocity. Now we have a time and a velocity. So we can calculate a distance that the surviving companion can travel within the supernova remnant's age. And we can define a search radius. And within this radius, we can try to identify the surviving companion by some peculiar physical properties. However, over the past decades, up to date, no confirmed surviving companion is found in the Milky Way. And more worse, there are not many type 1 supernova remnants in the Milky Way. So what should we do? We decided to push the envelope to other galaxies. And the first galaxies we choose is the Large Magellanic Cloud at the distance 50 kiloparsec. This is a close-up image of Large Magellanic Cloud. And I'm going to demonstrate that why we choose the Large Magellanic Cloud as the place to search for a surviving companion. So on the screen, there is a white dash rectangular region. I'm going to take a close-up of image of this region. This is the image obtained with the ground-based telescope. And you can see the resolution is not enough if you want to search for a companion star within a type 1 supernova remnant. It will be very, very difficult. So we change the telescope. This is another ground-based telescope, the CTIO 4-meter telescope. And now we can see here there is a complex environment. So I'm going to take another close-up image of the rectangular, the white dash rectangular region. Here is a type 1 supernova remnants. And our goal is to search for a surviving companion within this type 1 supernova remnant. But we can see there are so many bright dots in this image. Are they all stars? We want to search for a surviving companion stars, and it looks still difficult. So we use the Hubble Space Telescope, and this is an optical image H05 plus broadbands. And this type 1 supernova remnants called N103b. So now, here is the reason that why we choose the Large Magellanic Cloud to be the place to search for a surviving companion. Because at the distance of 50 kiloparsec, stars and supernova remnants can be well resolved, and the extinction is low, and the inclination angle is small. So from this image, we can notice that N13b is located in an unusual place, while type 1 supernova remnants usually found in a nowhere. N13b is located in the outskirts of a superbubble around NGC 8050, and it's a very complex environment. So our goal is to search for the surviving companion within these type 1 supernova remnants. However, N13b looks as a metric. So where is the explosion center? To define an explosion center, people usually use the multi-wavelength boundaries of supernova remnants to assess a explosion site. But it doesn't work for N13b. We can see here, this is a color composite image, and optical plus X-ray plus radio emission. We can see the first component. There is an optical H-alpha shell. The shell is open to the east, while the X-ray and radio emission extends further out. And there are some nebula knots, some strange materials inside the type 1, inside N13b, and we don't know what it is, what they are. And there is ionic gas in the background. So if we want to search for a companion star within N13b, we need to explain what we have observed. We took a high dispersion spectrum. So in this slide, there are 3 components have been detected. The first is the optical HO shell. And we can see in the optical HO shell has an enhancing emission in the HO lines, but without the counterpart of nitrogen-2. And this is a characteristic of a collisionist shocks called bomber-dominated shocks. And it requires a partially neutral ambient medium. So this detection answers the question that why N13b is located in this such a complex environment, while type 1a supernova remnants are usually found in the nowhere. Because N13b is not physically associated with the background ionic gas, because it requires a partially neutral ambient medium around N13b. So this is the first component we have detected. The second component is those materials inside N13b. We took the spectrum and used the SOBA2 double lines to measure the density. We found the density is very, very high, over 10,000 hydrogen centimeter per cube. And it's a characteristic of circumstellar medium. So the existence of circumstellar medium favors the accreting scenario. Our final goal is to differentiate its accreting or emergent. And the existence of circumstellar medium favors the accreting scenario. So it's worth to search for a surviving companion within N13b. At the same time, we noticed that the circumstellar medium has bright HO emission, as well as the bright forbidden line nitrogen-2 emission, and with large velocities spread. And the third component is the ionic gas along the slit. So to explain what we have observed, we propose that the initial binary system of N13b has a large proper motion through the interstellar medium. So you can see there is a compression on the leading side, and there is a low density in the trailing side. And it's a accreting scenario. It originates from a accreting scenario. And the circumstellar medium form an incomplete torus within the N13b. So instead of using the multi-wavelength boundaries of N13b to define a supernova explosion center, we adopt the bomber shell center as a supernova explosion center. You can see the bomber center is derived from the white dash curves. And we can see that because if the supernova explosion centers are different, the candidates of surviving companions will be different. And this is a new method to assess the supernova explosion center. So now we are going to use the images and spectrum of stars to identify the surviving companion. And using the images of stars, we can make the photometric measurements of underlying stellar population. And we construct the colorimetric diagrams of stars. And we can compare the locations of stars in the colorimetric diagram with the evolutionary tracks of surviving companions. In the left panel, these evolutionary tracks of surviving companions are simulated by Professor Pan Guoquan in National Tsinghua University. And the right panel is another model by Posiadowski in 2003. So as a result, we find that star 1, the star that close to the explosion center, has a temperature and luminosity consistent with the one solar mass surviving companion in comparison with the Posiadowski's model. And this is the first possible surviving companion outside the Milky Way. So it has been said a picture is worth 1,000 words, but the spectrum is worth 1,000 images. So we further use the VLT-Muse observations to get the spectrum of stars. So the Muse observations is a data cube that there is an image in the X and Y axis and the spectrum in the Z axis. So we can get the spectrum for every point of this data cube. And after extracting the spectrum of stars, we can do the fitting and get the more stellar parameters that we want. And the radial velocity is consistent with the expectation. But we didn't, but because the absorption lines of the stellar spectrum is contaminated by the strong emission, nebula emission lines. So some detailed analysis we are still working on. So these are 5 youngest supernova, type 1 supernova remnants in the Large Magellanic Cloud. In this presentation, I will show the results of search for surviving companions and circumstellar medians in these 5 type 1 supernova remnants. And why these 5 type 1 supernova remnants are important? Because these 5 are the youngest. And more younger a supernova remnant is, then less distance a surviving companion can travel, and much easier to search for a companion star. So from the left to the right is with respect to the age. And you can see the size is roughly from the small to the large, because when the supernova remnant becomes older, the supernova shocks will go through the interstellar median, and the size becomes larger. So I just show you the results of search for surviving companion in N13b. That is the middle one. And I'm going to show others, the results of other type 1 supernova remnants. This is 0509. And we can see that it has a very regular shape. And this is the ideal case for the type 1 supernova remnants. It not only has a regular shape, but also are found in nowhere, not like N13b that is located in a complex environment. So this is the only one that confirmed merger scenario, because near the supernova explosion center, there is even no any stars near the center. But when we analyzed these type 1 supernova remnants, we found a faint patch just at the location of the supernova explosion center. And we took the spectrum and found, in fact, the faint patch, in fact, is a galaxy, a background galaxy. And we call this photobomb galaxy. It's just a coincidence that the galaxy is located at the near the center of 0509. And this is 0519. And we use the images and spectrum of stars. In the middle panel, we construct the colorimetric diagrams of stars and compare the location of stars in the colorimetric diagrams with the evolutionary tracks of surviving companions. And we didn't find a star that matched the expectation. But in the right panel, we took the spectrum of stars and we measured the stellar parameters of stars and get the radial velocities. We construct the radial velocity distribution of the underlying stellar population. And we can see the mean of this velocity distribution is roughly about 270 kilometers per second. And that is consistent with the radial velocity of the Large Magellanic Cloud. In the meantime, we find that star 5 has a radial velocity that is larger than 2.5 sigma relative to the mean of this distribution, and make this star is a possible surviving companion. It's interesting to talk about DML71 after 0519, because in the middle panel, we didn't find any star match the expectation neither. But in the right panel, we construct the radial velocity distribution of the underlying stellar population. You can see the mean of this distribution is also consistent with the radial velocity of the Large Magellanic Cloud. That is about 270 kilometers per second. And there is a star 80 that has a radial velocity with larger than 2.5 sigma of the mean of this distribution. So star 80 is also a possible surviving companion. So this is the oldest type of supernova remnants in our sample. It's about 10,000 years. And we can see that there are too many stars in the colorimetric diagrams. So 10,000 years may be a limitation that we can search for a surviving companion within a type 1 supernova remnants. So now we found possible surviving companions in these 3 extragalactic type 1 supernova remnants. And this result raises a question that does N13b the only one has dense circumstellar medium? We can see that there are dense materials inside the N13b, but it looks not in 0519 and DML71. So this is a previous slide that I just want to recall that in this slide, we detect 3 components: the optical HO shell, and the circumstellar medium, and the background ionized gas. And we noticed that the circumstellar medium in N13b has bright HO emission, as well as the bright forbidden line emission, with a large velocity spread. So intrigued by N13b, we search for forbidden line emission in these 4 type 1 supernova remnants. And these images are optical images, just with the X-ray emission removed. So the red color represents the HST H-OVA. And it looks nothing in 0519 and probably DML71, but there are materials in N13b as well as the 0548. So we use the VLT Muse observations, and contrary to expectations, we are persistently found that there are strong forbidden line emission in all these four type 1 supernova remnants. So the yellow color represents the VLT Muse sulfur emission. And we can see there are so many materials in N13b and DML71. And there is also 2 small knots in 0519. And for 0548, we don't have a complete field of view observations. So we only have these 2 rectangular region observations. but we can also, but we have also detected a strong forbidden light emission here. And by using the solver 2 doublet, we measure the density of these materials. The densities are very high, and they are it's the characteristic of the dense circumstellar median. And the existence of the dense circumstellar median favors the accreting scenario. So we analyze this circumstellar median, and we plot the SOBA2 ratio of this circumstellar median in this plot. So we can see that there is a, you can see the x-axis represents the density, and from the left to the right is from dense to less dense. And we can see there is a clear separation between the circumstellar median and interstellar median. The circumstellar median has much higher densities. And in the meantime, that we found that the physical properties of this circumstellar median appear to reflect an evolutionary effect. That the density of the circumstellar median in different type 1 supernova remnants, when the type 1 supernova remnants become older, the circumstellar median inside becomes less dense, and these results make sense. And so the presence of a circumstellar median in type 1 supernova remnants could be more prevalent than people previously thought. So here are the line images that we compare with the accreting scenario versus a confirmed merger scenario. For N13b, we have detected the dense circumstellar median, and we found a possible surviving companion. And for the 0509, the right panel, there is no circumstellar median, and there is no surviving companion, and even no any star near the center of these type 1 supernova remnants. The upper panels are the HST and VLT muse H alpha, and the lower panel are VLT muse oxygen and sulfur emission. And we can see while N13b has strong emission, on the circumstellar median of N13b has strong emission in all line images, but the 0509 only the shell of 0509 has strong H alpha emission, but without any counterparts of the forbidden light emission. So it's a big difference between the accreting scenario and the merger scenario. So this is the summary. We try to figure out is accreting scenario or merger scenario for type 1 supernovae, or both they are correct. So we push the envelope from the Milky Way to other galaxies. In 2017, using imagery of stars, we find the first possible surviving companion outside the Milky Way. And in 2019, using images and the spectrum of stars, we find the first spectroscopic identification of possible surviving companions outside the Milky Way. And then we study the physics from compact stellar objects to diffuse gas, using the images and the spectrum of stars, and also the type 1 supernova remnants. We analyzed the physical structures of the supernova remnants. We reported the first detection of dense circumstellar median in 3 extragalactic type 1 supernova remnants. And the physical property variations of the circumstellar median appear to reflect an evolutionary effect. The circumstellar median becomes less dense when the type 1 supernova remnants becomes older. So the origin of accreting white dwarf for type 1 supernovae could be more prevalent than people previously thought in the Milky Way. Thank you.
Thank you very much. Any question for Chuan-Jui? Any question? Shiwei, please.
Hi, thank you for very interesting talk. So I'm question about the final point, the summary. So here you show a fraction of accreting and mergers. So what's the sample size to derive these fractions?
This fraction is derived by the observations of the type I supernova remnants. So in the Milky Way, people search for surviving companions and circumstellar median in the galactic type 1 supernova remnants. But they found that the accreting scenario may be just up to 20%. So we carry out, we search for surviving companions and circumstellar medians. That we use two different methods, try to answer the question, accreting or merger in the large Magellanic Cloud. And we carry out these studies for the 5 youngest type 1 supernova remnants in the LMC. And we found that according to the results of detection of the circumstellar median and possible surviving companions, it's about 60 to 80% are from the accreting scenarios.
So that's for LMC, that's based on the result 5 sources, right?
Yes.
But how about Milky Way?
It's roughly 5.
Also 5.
Yeah.
Do they have a comparable like ages?
You mean the age of type 1 supernova remnants?
Yeah, in Milky Way, the sample here.
Yes, yes.
Okay.
They have a comparable age, but the number of type 1 supernova remnants in the Milky Way is not many. So if we cannot find a surviving companion in the galactic type 1 supernova remnants, then we need to extend our study to other galaxies. And that is the reason that we carry out the studies from Milky Way to the large Magellanic Cloud.
Okay. Siwei, do you feel okay?
Yeah, thanks.
Thank you.
Thanks. And Ding-Wan, please.
Thank you for your talk. Can you hear me?
Yes.
Yeah, so maybe I can do a follow-up question. So from theory, do we have any expectation on the numbers? Like what's the fraction for the merger scenario and what's the fraction for accreting scenario based on theory?
It's a good question. And I think probably it's hard to answer because from the observation view, you can see the difficulties that we can differentiate accreting or merger. So for these two scenarios, they all have pros and cons. So they have these advantages and disadvantages. But up to date, in the Milky Way, that people thought the accreting scenario is less than 20%. So more studies favors the merger scenarios. And our study show that this fraction could be different from the people previously thought.
I see. So for example, based on this slide, the Milky Way, it's 80% is merger based on your observation, right?
Yes.
So I'm curious. I probably missed at the beginning. So I wonder whether or not there are light curves. I have some difference, or actually based on light curve, we cannot distinguish the two at all.
Oh yes, it's a good question. To answer this question, for example, that for the accreting scenario, one advantage is that we can easily simulate the conditions, and it will be more easily to confirm that is a accreting scenario. But for the merger scenario, the most common conclusion is that nothing will left. For example, in a accreting scenario, people expect the existence of the surviving companion and circumstellar medium. But for the merger scenario, people expect nothing will left. So if we cannot confirm this one is a accreting scenario, then the most likely possibility is the merger scenario. But the difficulty for merger scenarios is that it's very difficult to confirm, to say it's because of blah blah blah, and so it's merger scenario because nothing left. We can only say it's not accreting, so it's probably a merger. So back to the question about light curve, that people can search for some signature produced by the interactions between the, for example, the supernova ejecta and the companion, and there will be some signature left in the spectroscopy. So this is the method that we can differentiate is accreting or merger scenario.
Sorry, so you say from the light curve, they could be different.
From the spectroscopy, I remember there are some lines were different.
Okay.
Yeah, but if you ask about how the magnitude decay, then I'm not sure right now.
Okay, I see. Because I'm asking just based on cosmological point of view, that when people using the type 1A as a standard candles, and in the past, I all learned is like based on the accretion scenario, and as you mentioned at the beginning, that people use them as a standard candles. I just wonder whether or not currently, I suppose people are just mixing the two scenarios together to use them as a standard candle, and I just wonder whether or not if there's a way to separate them, whether or not we can maybe decrease the systematics in terms of cosmological measurements or something.
Yeah, it's a good questions and an issue that was discussions. Yeah, because the type 1I supernovae are used as standardizable candles to prop the cosmological distance. But in fact, there is an issue is that the more type 1I supernovae seems to have more diversity in recent years. We found many diverse type 1I supernovae that has properties that are different from the standard type 1I supernovae, like type 1AX or some subclasses type 1I supernovae. So for the accreting or merger scenarios, they are both have advantages and disadvantages. For example, for the accreting scenario, at the very beginning, people expect that when the mass of the white dwarf reach the Chuan-Jui mass, about 1.4 solar mass, it will explode as a type 1 supernova. So it can explain the consistency of the consistent peak luminosity of type 1 supernovae. But up to date, we cannot find a surviving companion in the Milky Way, for example. So there are more and more theoretical models try to explain what we have observed. So consider the momentum, like spin up, spin down models. So the mass of the white dwarf to explode as a type 1 supernova can over or can below the 1.4 Chuan-Jui model, called the super Chuan-Jui model or sub Chuan-Jui models. And for the merger scenario, the mass of the white dwarfs to explode as a type 1 supernova can also over the 1.4 solar mass, and it can probably explain the diversity of type 1 supernovae. But it also challenging, like the light curves you mentioned, that what we have observed.
Thank you.
Yeah.
Thank you. So actually, I want to have some substantial comments about this part. I mean, the light curve itself from the type 1a, basically, we cannot distinguish is from the single or double degeneracy. That cannot be distinguished. And the original model for 1a explosion is from the accretion white dwarf is because we think about the binary case, and the accretion is a very good way. And the problem is we see the type 1a explosion, but when we look back into the image, we cannot see the progenitor star because there should be a red supergiant, and then this should be a reasonable luminous star before the explosion, but we just cannot see it. So that's people was wondering, oh, maybe it's not due to accretion. Also, people think about the double neutron star mergers. The key thing about the 1a light curve is because it will be produced roughly from 0.5 to 1 solar mass of nickel 56. That power the luminosity of the 1a. And no matter whether you do it from accreting binary or from the merger of the binary, you have a similar result. So light curve cannot be distinguished. But there are other ways to distinguish. Just like Chuan-Jui mentioned about the spectrum, some of the composition part. But that won't affect the cosmological measurement about the distance. Because in cosmology, there's a so-called, in the 1a, there's a very nice relation called Fields relation. So it tells you basically the width of the light curve and the luminance of the light curve. And then you collect all of these different diversity 1a, it will give a nice fit of the curve. So that's why 1a can be a standard candle. It's just similar, like people don't actually know about how the 1a explode, but they can use it as cosmology. Just like a fast radial burst. People don't know how to generate fast radial bursts, but you can do the cosmology to measure the missing baryons, for example, in cosmology. So that's some of these sorts. And still study the explosion mechanism for 1a still is a active research area. So we will see and we will get more result. But I would like to comment about Chuan-Jui's the final conclusion about the ratio between the accreting binary and the merger case, the ratio. I think that result is most likely due to the observational bias. Because you have no good reason about what caused the difference between the LMC and the Milky Way, why this ratio is very different, because the percentage is just quite different. So I would like to say, just you don't have enough sample of the 1a. That's my point. So
I have a comment that about the fraction between the Milky Way and the Large Magellanic Cloud, because it's possible, because we know that type 1a supernovae originates from white dwarfs, so it will be related to the stellar population of the galaxy, and we know that the metallicity of the galaxy and the Large Magellanic Cloud are different, and with other different the parameters of the galaxy. So the stellar populations will be different, and it will have impact on how the white dwarf explode as a type 1a, how the white dwarf will form. So the fraction between different galaxies can be different. I think for me it makes sense.
Yeah, let me comment about this point, and then we'll allow please wait for a minute. So the thing is about the metallicity effect. As I totally agree with metallicity effect on the stellar evolution model, because we are working on these things. So we know about how metallicity affect the evolution of star and their supernova. But the key thing is about, you think about those are the white dwarf stars, and they're from mainly from low massive stars. And then you look at the INF initial mass function among all the galaxies with different metallicity. It shows the saltpeter IF is really a nice INF to explain the distribution about the mass and numbers. So you think about this from the few solar mass star, and then usually we have a lot of cases that might be have become binary and may have a 1A and may have both have double degenerates or single degenerates. That's naive thinking and try to get this kind of think about the expected result. And then, please.
There are so many things we don't understand about type 1A supernovae, and we've been searching for type 1A supernova remnants in M33. So if anything at all, M33, the mass and everything is very similar to the Large Imaging Cloud. It's even more massive than Large Imaging Cloud. In the Large Imaging Cloud, we have 5 young type 1A supernova remnants that are bomber line dominated. But in M33, 0. We didn't find any. So there are some kind of systematic differences between M33 and the LMC, the type 1A supernova remnants. We use the supernova remnants to diagnose the type 1A supernovae, things like that. So there's something fundamental different, and we don't know what is different there. And so there might be different pathways that go into type 1A supernovae. We just don't know what goes into what.
Okay, thank you.
Yeah, so thank you, Ken. Thank Ken for comments. And so I think we are working on to extend our studies to other galaxies as well, not only the Large Magellanic Cloud, like Lao said. So yeah.
So I was wondering if the JWST can help you to boost the sample size, maybe to further galaxies. How do you think?
I think the JWST we can use is to try to understand the physics of the explosions, and especially about the dust, how the dust can produce and what kind of dust. So it's a good directions that I was thinking about to that could JWST be used to understand, I mean, the initial binary system of the type 1 supernovae.
Okay, sorry, there's any other questions?
But JWST cannot see stars.
Can JWST see stars?
No, it cannot see stars. It can only see the very nearby bright stars in our galaxy. Only the very bright star, only the very nearby stars. Those are the wavelengths. The stars do not emit in those long wavelengths.
Yeah, JWST was infrared for long wavelength design. Yeah.
We still love Hubble.
Yeah. And Chen Songqi.
Yes, can you hear me?
Yes.
Yes, I have a question about I'm just curious about how is the age of the supernova remnant derived?
So when the supernova, I mean after the supernova explosions, the supernova shocks will go into the ambient medium. So normally, when it becomes older, the size will become larger. So we can use the shock velocity and so on to derive the age of a supernova remnants. And this is just one of the methods. Yeah.
There's another direct method that's using light echo.
Yeah, to measure the light reflect from the supernova explosions and the time the different light derived the observer will be different. So we can calculate the difference and get the age of the supernova remnants.
Okay, thank you.
Yeah, thank you.
Any other questions? Han Song Han Li.
Yeah, I have a question about the circumstellar medium. So, so what's the origin of the circumstellar medium? Is that like something like stellar wind from the progenitor of the supernova? Or
Yes, it produced from the interactions between the initial binary system or the interactions between the supernova ejecta and the companion.
okay,
So
thank you. Okay, I have another question about the first supernova remnant, the N103, that one. So you just say so this have asymmetric supernova remnant shape, and you say that this is because the supernova have a velocity offset with the relative to the circumstellar median. And if it's the circumstellar median is originally from the progenitor, then these two must have similar systematic velocity. Then how do the supernova have velocity offset with the median?
So to explain what we have observed here, that we propose that because the presence of a circumstellar median, so the initial binary system of 103b is likely a accreting scenario. And this initial binary system has a large proper motion from the east to the west through the interstellar median. So it's like a boat in ocean. There is like a bow shock. So there is a compression on the leading side and a low density in the trailing side. And the circumstellar median form an incomplete torus on the initial binary system, the plane of the initial binary system. And from this spectrum, you can see the difference of the velocities. That because the circumstellar median was shocked by the supernova ejecta, by the supernova shocks. So you can see the second component, circumstellar median in the spectrum, has a large velocity spread. But for example, the optical HO partial, the first component, it doesn't have a large velocity spread.
Okay, so can you go back to the last slide?
This one? Or?
Yeah, so what's this large proper motion come from? What's the reason that this binary system have large proper motion with respect to the interstellar median?
It's a good question. And
so I mean, because these two must have similar systematic velocity, then how could they have a large velocity offset?
I don't know right now. I don't know at the moment.
Okay.
Hello, please.
There are two processes here. The circumstellar medium was ejected when the stars are still in the binary system. There's a common envelope evolution. So the envelope was ejected, and that causes this circumstellar medium. Then you have this tight binary. So when the white dwarf explodes, it loses a lot of mass. So it's just like a normal binary system. One star explodes, and the mass was ejected. The supernova ejecta is gone from the system. So it gives the star a kick. So it's a kick velocity that gives you this high velocity.
Oh, okay. Yeah. I see. Thank you.
Good. And one.
Excuse me, can you hear me?
Yes.
I'm now curious about since you have mentioned a lot about the envelope system from caused by the circumstellar medium, right? Am I correct? It's kind of an envelope evolution. Is that correct?
Could you say again?
The circumstellar medium form kind of an envelope cause some time evolutionary physics inside this kind of circumstellar medium circumstellar medium. Am I correct? Like
No,
laws of
no,
no,
stars
okay.
form it's very close binary. They form a common envelope. The
Okay.
envelope is ejected to become the circumstellar medium.
Okay, so they first form the envelope, and envelope like evolve into the circumstellar medium.
Right.
Okay, so what would be the time scale for this evolutionary process?
From the initial binary to type 1 supernova remnants, roughly mega year to 10 giga years, I remember.
Okay, so like that's a very strong like phase difference between like circumstellar medium with the interstellar medium. Like, is there like a huge phase difference that we can like clearly observe it? Something like that. Let me rephrase my question again. Like,
Okay, good second.
yeah, like during this, like when as long as we can observe this remnant, like is the phase difference between this remnant and the outside like interstellar medium has like a very strong like difference that we can like for example like clarify or like to clearly see it. I'm not sure whether it's possible.
I'm not sure what the phase you
Like
mean here.
For example, like temperature or
Yes.
or velocity or something like that.
Yes. The temperature and the velocity will be very different from the interstellar medium.
Okay.
For example, the density of interstellar medium probably even in this complex environment is less than 100 and 200 hydrogen per centimeter cube.
Okay.
But the second medium here, you can see is over 10,000.
Oh, okay.
Yeah, so yeah, we can, yeah.
Okay, thank you.
Yeah, thank you.
Good. Any other final comments? Questions? Okay. So if not, let's thanks Chuan-Jui again, and thanks everyone for joining. Thank you.
Thank you.
Good afternoon.
Thank you.
Bye-bye.
Bye bye.
Bye.